Hey everyone, and welcome back to the channel. Today we'll be talking about Redis in a little bit more depth than I have in the past, which is a technology for storing a bunch of data in memory. Now personally, I don't really need to keep a bunch of gigabytes of data in memory. The only thing that I really keep in memory are all of the traumas that I have had to endure throughout the duration of my life. And they actually keep me going pretty well throughout the day and the gym and work and making videos on this channel. So I only probably need a few bytes in total, but for those of you that need more, let's go ahead and talk about Redis. Okay, so today we're going to talk about Redis. This is going to have some overlap with some of the other stuff that we've said on this channel, but I think that caching and systems design interviews is something that I've probably focused on very little, relative to the duration of the videos themselves. So hopefully this one serves as kind of an explanatory video on how people tend to do caching in distributed systems. Cool. So Redis is a in-memory key value store. So it's an external technology. It's open source. At least part of it is open source. I'm mainly going to focus on the open source aspects of it in this video. And it can also be distributed to make a distributed caching layer. So Redis can do a lot of things. So, because this is ultimately a for-profit company at the end of the day, they're always adding features. And so I think a lot of people are going to come in here and be like, oh, why don't you use Redis as like a lock, or Redis for PubSub, or any of these other features. And I just don't really think it's the core functionality. And there may be other better technologies for some of these things. So I'm going to not address those in this video. Those are going to be considered out of scope. So things like PubSub, vector database, geoindexing, things like hyperloglog. It's nice that they have them, but I'm probably just not going to talk about it very much right here. So let's focus on caching specifically. So I guess question number one is when to use Redis. It's nice to have this kind of in-memory key value store, but what do we actually want to use it for? Well, typically the answer is caching. What do we use caching for? Caching is used for information that we access a ton in our distributed system, but if every single one of those calls were to go to a database, it would really slow things down. It would put a lot of load on the database. So specifically, caching is great when you have some percentage of your keys in an application that are accessed a whole lot, and you would prefer those to be served from memory. Because it's just going to speed everyone up and it's going to shield a lot of load from the database. So because Redis is kind of this external technology that is built by someone else and not your own application logic, typically it probably isn't getting embedded in the application logic. So what does that mean? For all those strategies that we've talked about for distributed caching in the past, things like read-through caching or write-through caching or write-back caching, where you've actually got some sort of caching layer in between the server and the database, right? So for example, in write-through caching, when a server makes a write, it's going to Redis and then to the database at the same time. And similarly with write-back caching, it first goes to Redis, maybe it gets buffered a little bit, and then it goes to the database. Now, that's not really something that you would use Redis for in practice. The reason being that, this is software that someone else wrote, and you can't just import your own application logic in there. Now, it seems that, someone's going to correct me. In recent years, they've added this thing called Redis Gears, where you can actually put in some of your own application-specific logic in there. Though it doesn't really seem like, from what I can tell, it's super popular. I'm sure a lot of developers are not going to love that you have to kind of deploy code to an external system like this. I feel like that's kind of a pattern that a lot of people look to avoid. So I'm going to mostly ignore that for now and say that generally speaking, the best time to use Redis is for this kind of read or write aside caching, which, to be clear, is not a two-phase commit, right? So technically, write-through caching can be done where this write to the database and this write to Redis are executed atomically with a two-phase commit. But that is not going to be the case here. The point is either you're writing to the database first or reading from the database first, and then writing to Redis second or reading from Redis second. But the point is it's not transactional, right? You've got this information, you're loading it into Redis. If I'm a server and I want to read some information, maybe first I check Redis, and if it's not there, I check the database. And if it is in the database but not in Redis, then maybe I go back to Redis again and put it there, or something like that. There are many different ways that you can do this, and we've spoken about caching strategies exhaustively on this channel, so I'm not really going to do that here. But the point is, there are times to use Redis, and there are times to kind of build your own embedded distributed cache using an embedded caching library, and this probably isn't one of them. Okay, so just to give a quick overview of what we're going to actually get into in the video itself, we've got TTLs and eviction policies that we want to talk about. So this is basically all the single instance Redis features, the things that you can do with the key value store itself. Then we'll talk about actually scaling out Redis via both replication and partitioning or sharding. Cool. So basically, because Redis is cache and we're storing data in memory, we only have so much memory and we want to conserve it where possible, because the more information that you can fit in your cache, the more useful that cache is. You're going to get better hit rates. So what we can do is, if a key has been there for a while and, it's not really getting accessed very much, we can set a TTL. So maybe we'll say delete this key in 1 week if no one's accessed it in that time. And that's just going to help us reclaim some free space. Just in general, we can also say per Redis node, hey, here's how much memory we're allowed to use for this cache. And then if we hit that limit, we'll start performing evictions. So Redis, like the majority of caches, has a variety of different eviction policies that you can use. So I list 4 over here, but each of them kind of have 2 classes. There's the all class and the volatile class. So basically what that means is the all version of them will, consider all keys that are stored in their eviction policies. And then the volatile version is basically only going to consider keys with TTLs as ones to evict. So you can optionally not provide a TTL for a given key, and in that case it will actually never get evicted. And then you'll only look to evict the ones with TTLs. So basically we have least recently used, we've got least frequently used, we've got random, and then we've also got this concept of a TTL policy, where basically, obviously we're going to get rid of keys when they expire, but also if we have to evict keys and we have to choose which one to evict, choose the one with the TTL that's closest to expiry. So obviously that's only going to work for the volatile approach, not the all approach, but you guys get the point. Basically, the Redis official doc suggests, hey, you should probably just use LRU in the majority of cases where, some of the keys are going to be really hot and the others you can probably just get out of there and churn them out. But if your application, for whatever reason, understands that certain keys should be removed at a certain time, then maybe their TTL logic is really, really good, and in that case, maybe you want to use the TTL eviction policy. So when would that work? Maybe something like a newspaper site where they're like, all right, we know that in 3 days from now, this article is going to be completely irrelevant, so why don't we give this thing a TTL of 3 days, and it'll just get out of there when we need it to. Okay, another thing we're going to talk about is Redis transactions. So basically, Redis does run on a single-threaded model, which is really great. That being said, without transactions, what could happen is, I could submit 3 different requests over the network to Redis, someone else could submit 3 different requests over the network to Redis, and they could get executed in interleaved order, meaning that we don't actually know the final serialized order that they get executed in. So that could cause a variety of issues and race conditions that, again, we've spoken about a lot on this channel, but here's how you would avoid them in Redis. Basically, if you want to do something like a pessimistic locking, or execute those instructions atomically and not let anything else get in between, and also physically stop them from getting in between, you can use the multi-statement. So the multi-statement is just going to say, I have these 3 operations, let me send them in batch over to Redis. Redis is going to execute the 3 of them, and then it'll allow other operations to proceed. There's also this concept of a watch keyword. So the watch is basically a compare and set. This is going to be optimistic locking because, I can submit a command and then, 10 seconds later say, if the value of this particular key is what I thought it was 10 seconds ago, then execute this other command. And so it's conditional, right? You won't execute it if the value has since changed, but you also don't need to lock away other operations from performing whatsoever. Okay, now we're going to talk about durability of data. So on a single node, everything is still being stored in memory primarily, but that means that if the node crashes, we're going to lose it all. So what are our options? In traditional databases, you would use something like a write-ahead log. So in Redis, that's called AOF. It's called an append-only file. And basically, similarly to something like Kafka, you can basically control how often those entries get flushed out to disk, because otherwise, if you flush them super often to disk, it's going to be pretty expensive, but if you flush them not very often, that means that on a failure of the Redis node, you may lose some data. So that is something that's ultimately configurable. They recommend 1 second for a good trade-off between performance and data loss. And then another option that they have is called RDB, short for Redis database, and this is basically, every 5 minutes or so, snapshot the entire data set, store it to disk, and that way you can do backups really easily, or if you fail over, instead of having to replay this entire massive write-ahead log, it should be compacted, but it could still be fairly large, you restore from the snapshot and then maybe apply any write-ahead log entries that you have. So you can use both of these, you can use only one, you can use neither of these, but they are options that are available to you, which is important because when you're caching, sometimes you do actually want some data durability in the event of restarts. Even though your cache shouldn't necessarily be the source of truth, it's still nice to have because otherwise you're going to get a lot of cache misses on a restart. Cool. The next thing we'll talk about is replication in Redis. So we've spoken about Redis as a single node key value store so far, but also eventually we want to make this a distributed system, right? That's what this channel is all about. And so part of that is we have to replicate nodes so that if they go down, or for, if there's a network partition or something like that, we can, fail them over and still proceed like normal. So basically, Redis is going to use single leader asynchronous replication, which, as we know, means that all writes go to the single leader, reads can come from the single leader and be up to date, or perhaps, and in Redis you can do this as well, you can read from the replicas, but those reads may be stale. Another thing about single leader replication, especially when it's asynchronous, is that you can actually lose data, right? So because it's asynchronous, it's possible that I write to a leader, and then the leader fails before those writes get propagated back to replicas. Another possibility is that, for example, I have some sort of network partition, which I'm going to diagram down here. So we have some network partition, which is going to stop our leader from communicating with its follower nodes right here. So the way that Redis works is that the followers and the leaders of a given partition are going to create some sort of quorum, and that quorum is going to determine who the leader is amongst them, right? So let's say we have this leader, and the way that it works in Redis is you have a leader lease. So we have some lease that's going to expire at a certain time. The time between votes to choose the leader is something that's configurable within Redis. And basically, let's say the next vote is at t equals 110. So that means if I'm a client and I'm writing data at t equals 100 and there's this network partition here which stops any of the data being replicated to those followers, the client is going to be seeing that all of its writes are successful, but only at t equals 110 is this lease going to expire. Let's say this guy becomes the new leader, and then the new leader is not going to have any of the writes from t equals 100 to 110. So basically, whatever this timeout is that you can configure, this configurable timeout before the new leader election, which is called, I think, the node timeout in Redis, you can lose that many seconds worth of data due to a bad network partition, so keep that in mind. You can make that timeout really, really short, but what that means now is that all of these replicas are going to be sending lots of heartbeat messages between one another, and in theory it could degrade performance or saturate your network a little bit. Okay, I'm now just going to kind of spit out a potpourri of random facts about Redis replication that I didn't really have a good place to put. So let's go ahead and do those quickly. Like we said, Redis replication is generally going to be asynchronous, but you can make it synchronous by using the wait command. So basically that's going to force a write to be acknowledged by replicas before the client goes ahead and receives an acknowledgement. If a replica does fail, we're going to automatically fail over. And, similarly, if a replica now needs to go back to the master and get any writes that it's missed while it failed, it can do basically a partial or a full resynchronization depending on what data it already had before. So if it's like super behind, it'll just be like, you know what, give me the full state. If it's only a few entries behind in the write-ahead log, it can be like, just give me the entries that I'm missing. Additionally, when you're doing replication, you should definitely be using one of the persistence options on Redis, right? So that's either Redis database or the append-only file. The reason for that is that if I'm a master, I can fail and come back up without there being a new leader election. So I can fail, come back up, and still be the master of my quorum, or the leader of my quorum. And so if that were to happen, but I were to also lose my data during that time, now all of a sudden I'm going to replicate the fact that I have no data to all of the other replicas that care about me, and they're going to say, oh, I guess we're empty too. So you definitely want to be sure that you are persisting data via either snapshotting or the append-only file. Worth being noted that evictions, because they rely on an actual timestamp, right, TTLs, evictions was kind of a poor thing to put here. I should say TTLs. So TTL evictions rely on a timestamp. So obviously the clock isn't necessarily going to be completely synchronized between the leader node and any of its read-only replicas. So basically the leader node is also putting in its replication log, hey, I evicted this thing due to a TTL, and then the replicas will apply those. If they're serving read-only queries, they can use some sort of like logic on their own end to try and interpolate when an eviction should happen. But for the most part, the source of truth about when TTLs get executed is going to be the leader node. And then that kind of implies that, if you're doing these kind of read-only commands, those can actually be handled by replicas as well, but you may get stale data. So that is an option in Redis too. Cool. Finally, let's talk about sharding. This is going to be the last kind of important piece of the video. So basically, one really nice thing or one interesting thing that I like to highlight about Redis, because I think it's just a cool approach to handling sharding, and we have discussed it before, is the fact that they always use a set number of partitions of data, 16,384. So even if I'm only holding a couple gigabytes of data, I'm still going to have a ton of really, really small partitions. The reason that that's so useful, we'll talk about in a second, but first let's just go over some high-level facts. So to determine which bucket a key lives in out of the 16,000, we just hash it. And then additionally, sometimes your data models are just organized in a way such that, you want two keys to be co-located, but they don't actually look the same, or, they're not the same value. So there's this concept of a hashtag in Redis that basically you say, okay, here's this like other part of the key. You're actually going to hash this part of it, and that's how we're going to determine which bucket it's in. So it just gives you a little bit of flexibility so that you can, configure partition information without having to actually change the underlying data itself. We're using gossip in Redis cluster to basically dissipate cluster information. So the source of truth about which partition lives where is dissipated over gossip. Clients themselves can cache that information, but ultimately what they may end up doing is making a request to a Redis node being like, I think this partition lives here. The Redis node is then going to respond and be like, nope, that's not true. This is a little bit different because in some systems, that Redis node would maybe proxy that request to another node in the cluster. In Redis, they're just going to redirect the client. So they'll go back to the client and say, nope, you should reach out to this other node. The client will do that, and then they'll complete their request. And then finally, we talked about transactions earlier, right? That's going to allow us to execute multiple operations atomically. The operations that they execute have to be on keys within the same bucket. There's no concept of distributed transactions here. There's no concept of two-phase commit. You need to organize your data in a way such that the data that you want to operate on together is co-located within the same bucket. Okay, so now we're going to come back to this guy right here. The question is, why are we using 16,000 set partitions? Well, the nice thing about using 16,000 preset partitions is it means that the hash range of the partitions themselves is never actually going to change. That means that moving them around is a lot more simple, right? Because any of the keys that are in one bucket, even if they don't yet exist in the Redis database, if that key were to ever be written, it will always be in the same partition, which is really nice for actually moving them around and rebalancing them. Now, at least in the open source version of Redis, you're only going to be balancing partitions or rebalancing partitions manually, right? It's like an operator thing that you can do with the CLI. But the point is, it makes reasoning about this a lot more simple than if there was some third layer system that were like constantly tinkering with the partition boundaries at every single step. That would make rebalancing them really, really tough. Okay, so now we're going to actually look at how moving partitions works in Redis, right? Because in theory, what you could do is you could just be like, all right, I'm going to move partition A from node 2 to node 1, and when I do so, I'm just going to completely lock it down, right? Like there are going to be no operations that are allowed to proceed on this thing, but that's actually not what Redis does. It operates in a way such that there's no downtime when you're moving partitions. So let's look into how they do that. So let's imagine I'm a client over here. I'm interested in one particular partition, which has keys A, B, C, and D, and I want to read the value of all of them. So in step 1, I'm going to reach out to node 1. Okay, so let's imagine that node 2 is transferring A, B, C, and D to node 1. And in the first step of the diagram, it's already transferred keys A and B, and it's still got keys C and D on its own. So basically, the way that Redis works is you can transfer a subset of the keys at a time within a given partition, so you don't have to lock all at once. It can be a gradual operation. So in step 1, the client knows that the partition is now supposed to live on node 1. Maybe gossip has happened, and it's aware of this. So it reaches out and says, okay, tell me what's the value of A, B, C, and D. And node 1 responds, okay, I have A, the value is equal to 1. I have B, the value is equal to 2. But for C and D, I don't have those yet. So you should go to the the node that's giving me that partition, which is going to be node 2 in this case. So that's what the client does. It goes to node 2 and it says, all right, well, now what's the value of C and D? Now let's say, sorry, mislabeled here. Let's say in the meantime that, between the time that the client is going from node 1 to node 2, node 2 transfers key C over to node 1. So client now reaches out to node 2 and it says, hey, what do you have over here? I'm interested in the values of C and D. And node 2 says, okay, well, I know the value D is equal to 4, but actually, wait a second, C is on node 1 again. So this operation of transferring a key C like this is atomic, meaning that if I'm a client and I'm reaching out to a particular node to get its value, either I know that it's located there or it's not and I know where it's now located. So in this case, the client is going to say, shoot, now I have to go back to node 1 to get the value of node C. It's going to do so, and then finally in step 5, we're going to see that C is equal to 3. And then at some point, D is also getting transferred over to node 1. Now the point here is, Even though I may have to jump around a couple times from node to node, ultimately it's a well-defined process that I'm just going to have to go to, the destination node or the source node a couple times each, and then I will certainly get the entire value of the partition. When everything is transferred over, then the entire cluster will be updated to say, all right, now node 1 certainly holds the entirety of this partition, and don't ever go back to node 2 to ask for it. Okay, so let's go ahead and conclude this video. Basically, Redis does have a lot of functionality, and people in the comments section of some of my videos will frequently suggest doing things like pub/sub or distributed locking or anything like that with Redis. I'm not saying you can't do that, and if it's something that you use all the time in your day-to-day job and you're really familiar with it, by all means, go for it. But at least as far as I'm concerned, I think its main usage within these videos is probably going to be as a distributed caching layer. And if it is, then I think there are a few features that we want to know about it. Number one is just when to use it, like the kind of write through versus write aside or look aside caching type of situation. Knowing the persistence options, right? Whether we want persistence or need persistence, and if we have replication and we have partitioning, how we should actually be setting those up. That comes along with things like transactions. If you want to write multiple keys to Redis at once, I could see someone just being like, well, how are you going to assure atomicity there? And you'll be like, well, I need to organize my data so that it all lies in the same partition, and then I can actually make sure that I get a transaction, ensuring that I update all of those keys at once. And then finally, partition rebalancing. I don't know that it's going to be super important to kind of understand specifically Redis partition rebalancing, but I think that understanding the tactic of using a set number of partitions from the beginning and rebalancing them over time such that you are only updating a set or a preset key range or preset hash key range at a time is a really, really useful strategy to understand. Anyways, guys, I hope you enjoyed this video. I'm heading out to Europe for a week, so I'm really looking forward to that, but it also means that I had to squeeze this one out a little bit early, and it's probably not my most high effort thing. Nonetheless, I hope it was still useful, and I will have to see you in the next one.